My name is Stuart Sierra. I work at Relevance and Clojure.com. And I came up with the idea for this talk, I don't know, maybe 6 months ago back at Clojure West, and I told Alex I wanted to do it. And you know, I had this idea in my mind, yeah, functional design patterns, that's a great idea. Then when I sat down to write this talk last week, I got a little nervous because I thought, you know, gosh, design patterns, that's kind of a loaded term. People have very strong responses to those words, mostly because of this book. This book has an ominous reputation. It has an ominous name, the Gang of Four. Sounds like, I don't know, a dangerous cult or something, or worse, a Senate committee. So it's actually a pretty good book, you know, given what it was trying to do and when it was doing it. You know, it's very, very tied to the world of C++ and object-oriented programming, but it does describe some useful ideas as starting points. And then, of course, it got corrupted by a lot of people who misapplied it. But this whole idea of design patterns has sort of gotten short shrift in dynamic languages and functional languages. People have even gone so far as to say that design patterns are a flaw in your language. If you need design patterns, your language is broken. And you know, in the late 90s, Peter Norvig gave this talk where he talked about design patterns in dynamic languages, and he said 16 out of the 23 patterns in the Gang of Four book are either invisible, they don't exist at all, or they are substantially simpler in a dynamic language, and his examples were Lisp and Dylan. But then in the same talk, Norvig goes on to say that once upon a time, the subroutine call was just a pattern. If you were writing machine code, you wanted to call a subroutine, you knew you had to push some values onto a stack and then jump to another piece of code. So patterns can exist at all different levels of programming. Now, I'm not going to talk about the original 23 patterns in the Gang of Four book. That's been done to death. I might mention a few of them peripherally. But I'm going to try to talk about some patterns that show up differently in functional languages, in particular Clojure. I'm also not going to talk about this. Are there any Haskell programmers in the audience? Yeah, okay, you're going to be pissed because you're going to be looking at my code examples and saying, ooh, that's a monad, and yeah, I know. But the thing with monads is, while they're a very powerful conceptual framework for describing computation and describing programs, I personally don't find them useful for explaining them. As a learning aid, as a tool for describing these things, I don't find them helpful, even though, as you will see, some of the patterns I talk about are actually monadic in style. So what am I going to talk about? Well, there's another book called Pattern-Oriented Software Architecture. It's actually a whole series of books. And I'm going to use their definitions for different categories of software patterns. First, there are the architectural patterns. These are the big, broad things that can describe an entire computer system. And they're frequently almost agnostic about what programming language you're writing in. That's pretty much irrelevant. They're talking at a level higher than that about how all the different subsystems and components fit together. Then there are design patterns, and this is what people tend to associate with the term patterns in software. They're thinking about these patterns that describe how things happen within a single component, how a program is structured, how the data flows, how the execution flows, things like that. And then finally, the pattern-oriented software guys talk about idioms, which in their definition are specific to a single programming language. They could be examples of a design pattern, or they could be just smaller, more localized patterns that are seen in a particular programming language. So this talk is somewhere in between idioms and design patterns. I have done all of my examples in Clojure, so you could say that some of these are idioms. But I think that some of these patterns I'm describing are also more generally applicable to any functionally styled programming language. So really anything that has first-class functions, any language like that can implement all these patterns. So after that long and somewhat apologetic introduction, here are the patterns. Anybody recognize that? That's magnetic core memory. I took that picture at the National Museum of Computing in England. I just thought it was cool. So that moved. Okay. In functional languages, a lot of discussion, a lot of ink gets spilled talking about state. How do you manage state? And built into that assumption is the idea, I think, of immutable data, that you can represent something that changes as a series of immutable data structures at different points in time. So one of my favorite patterns, and probably one of the most common ones, is what I call state event. Now, there are different names for this. Sometimes it's called event sourcing in different contexts. But the basic idea is that you have some system that has some internal state that you need to keep track of, and it has maybe a wide variety of inputs that can affect that state. And you want to be able to recover both the previous states of the system and possibly the inputs that caused the system to enter that state. So this is very simply a pattern of a single function, a function that takes the current state and some piece of input and then returns the new state. You know, by itself, it doesn't look like very much code, and it isn't, but it's a surprisingly powerful idea, because when you have your state represented in this way, you can do all kinds of cool stuff. The most interesting one is that you can take any collection of inputs and reduce over them. Remember, reduce takes a function that takes two arguments, the result and a single item. So you can reduce over all of your inputs and get the final state. And if you store all of the inputs, then you can automatically rederive any past state of the system. So this has all kinds of neat consequences. It's great for testing. You can, if something goes wrong, you can just sort of replay the events up until the point where things went wrong and then decide, okay, you know, look at that state at that moment and figure out what happened. Obviously, it's great for logging because you already have some data structure that describes every input to the system. You can make assertions across a whole series of events. You can say if something happened over here, then at some time later, this thing over here has to happen. And you have a lot of flexibility with this pattern about how you're actually going to store your state. At one extreme, you could say, well, I'm never going to store the state. I'm only going to store the inputs, the things that I can't reproduce. And so then you just know the result of all of those inputs is always calculated by a pure function. It's always going to be the same, so I can repeat that calculation anytime I need the current state. But of course, there is a downside to that. You end up repeating a lot of these calculations over and over again. But then there's another nice property to this, which is that you can always cache it. You can cache any of those intermediate states and say, okay, I'm going to make a snapshot of my state here, and then as new inputs come in, I can keep calculating the new state from there. So you have a lot of flexibility. Probably one of the biggest downsides to this pattern is actually the fact that every input to your system or every event in your system is a data structure, which is the point. I mean, that's where you get all the power. But it also means you can end up with hundreds or thousands of these little tiny data structures flying around in your program. And just keeping track of all of those can get a little confusing. There may be some costs in memory as well, I'm not sure. So there's a way to extend this, and this is not quite as widely applied as the state event pattern. You'll see that in all kinds of systems. But this is something I call the consequences pattern, where every input to your system may produce multiple effects. It might be multiple side effects, like things that have to happen, or it just might be multiple state changes. And you want to be able to look at those state changes individually, validate them, test them, or perhaps visualize them in a GUI or some other representation. So the way this ends up looking is a function that takes the current state and some input. It might be an event like, the user clicked a button on a web page or something, or, something happened in your server farm that you noticed in your monitoring system. And it returns not a new state, but a sequence of new events. It's all just data. This is all just pure functions returning data, but they're returning things that describe what's going to happen next. So this is actually a very powerful pattern. It can actually implement a simple rules system. You can build a small rules engine on this. It doesn't have all the power of a full rules engine, but you can do quite a lot. Obviously, the downside is it's more complicated. You don't just have one event making one state update. Now you have the potential for a single event causing multiple updates. And you have to make some decisions here. You have to decide, do I want these things to be recursive? Do I want one event to trigger 3 more events, and each of those to trigger 3 more events, and so on, until eventually it bottoms out? Now that's a very powerful system then. Now you've essentially got Turing completeness in your consequences rules, but you have all the problems that come along with that. You have infinite loops, much more complex logic to understand, and you can get yourself into trouble more easily. One of the other problems with this pattern I've discovered is that if you have more than one of those consequence functions, you can't just compose them naturally. If you have functions that take in an old state and return a new state, you can chain those together very straightforwardly, and there's no problem. But these consequences functions are returning sequences of events, so they don't just compose. And this is where the Haskell guys are screaming, sequence monad, yes. So this is how I did it. You could do it with just a loop that has a collection of consequence functions. It's going to call each one on the initial state. Actually, it's going to call the first one on the initial state, get a series of new events, use those events to update the state, and then call the next consequence function on that updated state. Meanwhile, it's collecting all of the intermediate events that were being produced. So this is, a little complicated. This can get a little harder to reason about, but it does work. So now let's move from managing state to building up state. Anybody recognize that? That's a hard disk. It's about 3 feet across, weighs about 40 pounds. I got to pick it up. Kind of fun. And really, when I talk about building up state, what I'm really talking about is accumulators. And I think this is almost the essence of what computers do. This is why we write software, because we have a collection of data bigger than we can comprehend in our own minds. It's more information than we can get any useful decisions out of. So we want to take a computer that's going to read through all of those different inputs and eventually produce some result small enough that we can comprehend it, something small enough to fit in our brains. And so I call this accumulators. There are lots of variations of this. And this is really one of the essences of functional programming. We've all seen this. We can use sequence operations to iterate over a large collection. We can maybe do that lazily. And we have this big library of functions that does different things with sequences of inputs. And then usually at the end, we're going to call reduce. And that's what reduce does. It takes something big and somehow turns it into something small. So this has all sorts of advantages. Obviously, the input could be larger than memory. We could be lazily reading the input from some other source. And it means that the inputs are going to be processed in order. So this pattern, as I've shown it here, works if order matters in computing these inputs, which it might. The only problem with this, as it's traditionally implemented, sequences being reduced, is that it's linear. It really assumes, it has sort of baked into it at the bottom this assumption that you're going to deal with one input at a time. Now you can relax some of those constraints in certain circumstances, but the basic structure of this algorithm is almost always linear, so you can't parallelize it very well. So I'll take a short digression here on MapReduce. This is not necessarily a functional pattern, although you can represent it functionally. MapReduce, of course, here I'm talking about Hadoop and Google's MapReduce stuff and all of this thing that everybody's doing now under the heading of big data. But basically, it's an algorithm built around certain hardware characteristics, certain performance profiles. In particular, the idea that your problem is bound by the I/O speed of a disk, a spinning disk that is physically connected to one machine. And so everything about MapReduce and Hadoop and all that is optimized around the idea that you want to do the fastest thing possible with a spinning disk, which is reading a long contiguous stream of data. So MapReduce ends up looking a little bit different from the traditional map and reduce functions in functional programming. It looks like this. You have a mapper function that gives, given each of the inputs in order, and returns a sequence of, in the case of MapReduce, key value pairs. So this means because the mapper function is potentially returning 0 or more outputs for every input, that it can do things like filter, and it can actually combine some of the inputs. It can do a little bit more than just a straightforward map, a one-to-one mapping from the inputs to the outputs. And then the reduce function also returns a sequence of key value pairs, and the input is actually a key with a collection of values. So in the middle of MapReduce, and really the essence of MapReduce is this shuffle operation. Now this is just a very casual implementation in Clojure. It doesn't, this doesn't do all of the distribution and obviously in the input splitting that Hadoop does. But this is the basic idea. It's going to take all of the outputs from the mapper and arrange them so that they are sorted by key. And then it's going to call the reducer on one key and a collection of all the values that had that key. Now this is very general. All of the things that you can do with map and reduce, pretty much any arbitrary computation can be represented this way. But again, it's tied to a very specific optimization profile where you're trying to get the maximum amount of data locality and efficient performance out of these slow disks connected by a slow network. But that's already changing. We've got SSDs where you can read from any part of the disk in the same amount of time. And we've got storage connected directly to a fast network so that eventually all storage becomes local. So the rules are starting to change. And again, this is fairly new, but I think MapReduce as we know it right now is probably going to become less important as we have these different hardware profiles, different trade-offs that we're going to have to start making. So here's a different version of this. Clojure 1.5 has a new library in it called Reducers that implements a pattern that I call ReduceCombine. And the basic idea is instead of reading linearly through all of the inputs, let's assume that the inputs have some kind of tree-like structure and that we can divide them up. And that we can do some operation on some small piece of the input, get a result, and then get two of those results and combine them together in some operation that is associative, meaning just that the order in which we do those combinations doesn't matter. So it looks like this. We have a reducer function that looks just like the function you'd pass to reduce in traditional functional programming. It takes a result and an input and returns an updated result. And it also can be called with no arguments just to give it its initial value. So basically, this is just like calling reduce, but the function itself is going to provide the initial value to start with. But then there's this other function called the combiner. And the combiner takes two results. So now we don't have to assume that we're always adding an input to a result. We could build up an intermediate result from a bunch of inputs and then say, okay, now I need to combine the intermediate results to go up one level in this tree of computation that I've divided up. Now, this has some very interesting consequences, one of which, the most interesting one, is that it's very easy to parallelize this because it doesn't promise that we're going to read through all the inputs in order. It doesn't say, you're going to scan from the first to the last and map over all of them in sequence. It says, okay, you're going to map over a few of them and get some result, and then map over a different few of them over here, and then you're going to combine those together. It also has some very interesting properties about how you can construct these reduce and combine functions. One interesting thing is for certain very simple operations, reduce and combine can actually be the same function. Think about addition. If you add up a bunch of numbers over here and you add up a bunch of numbers over there, what do you do to combine those two sums? Well, you add them again. So they could be the same function. But it also means that you don't have to create the intermediate sequences that you get in classic sequence-oriented functional programming. Things like map, filter, mapcat, all of those sequence functions are creating some intermediate representation of their sequences in memory. Reducers don't have to do that because they don't promise that you're going to read through the inputs in order. So there is no actual structure, and there are higher order functions in the reducers library that can do the equivalent of map and filter without actually having to realize anything. They all get composed into a single reducer function. So now let's go back to a simpler pattern, something that's probably more familiar if you've worked with any functional language. I call this recursive expansion. And the idea is pretty simple. You have some result that you're building up, and there are a set of primitive things that you want to get as your final output. But you want to build up layers on top of those. So you might have one layer that maps directly to those primitives, but then you want to build another layer on top of that that maps to those intermediate representations. And you want to keep processing this until there's nothing left to do. And this is very common in Lisp-like languages. In fact, every Lisp-like language does this when it does macro expansion. Interestingly, this is also how transaction functions work in Datomic. They expand out into a set of primitive data assertions. So this is essentially what it looks like. This is the recursive expansion driver that takes some function, an expander, and some input. It calls the expander function on its input, and then if the expander returns the same result, if it didn't change anything, then we're done. We've gotten down to the primitives. Otherwise, we recursively expand whatever the output was, and we keep doing this as many times as it needs to do until we get to a final primitive result. This is almost word for word how macro expand is implemented in Clojure. So the only problem with this really is that it can get a little tricky to reason about. As you build up higher and higher levels of abstraction, you have more and more layers in your expansion tree. It gets a little hard just to reason about what the final result is going to be. And so that's where it becomes helpful to be able to step through the expansion one at a time. In a Lisp, you have functions like macroexpand1 that allow you to do that. So this is a very powerful pattern. So we've got state, we've got building up data. What do we do when we actually want to do something? We actually want to do some computation or have some side effects or make things happen. That picture is a punch card sorter. So I guess you could say I'm going back in time in my computing history here. So this is one of my favorite flow control patterns. If you saw my talk at Clojure West, this will probably be familiar. I call this the pipeline pattern. And the basic idea is just that you have some process that you want to go through, and it has a bunch of steps. And the primary challenge that you're facing, that this pattern helps you deal with, is how do I keep track of the order? How do I know what the actual flow of logic is through the program? Now, in order to do that, it helps if you have a big collection of functions, all of which have a similar input and output. So they have an input that has a particular shape. Usually in Clojure, it's a map or a record. And they're going to return something with a similar shape. So it ends up looking like this. You can define your large process as a very straightforward threading of execution through a bunch of functions. And each one of those functions is going to look in something like this. You know, it's going to take the input, pull it apart to get some pieces of information that it needs, and then make some modifications to the input and return it. Now, the great thing about this is that anyone can look at that code and see what it does. So, you know, even someone who doesn't know anything about programming at all can look at that sequence of steps and say, oh, yeah, that's wrong. You know, C should come before A. So it's a very readable design, and it is really helpful when you're working with a larger group and you want to be able to make it explicit what is happening in a particular computation. Now, the downside is it does sometimes end up being a little bit longer. The code to write this out, because each of those functions has to do its own destructuring and recreating the output, the code ends up being a little bit longer than if you just coded everything directly. But it's much easier to read. And you have a lot of flexibility here. You can insert new steps in there without breaking anything. You could do some logging or some diagnostics or anything. It's also very composable, because the result function, that large process function, which is really just the composition of all the subprocesses, you could take that same function and use it to use it as a step in another pipeline. So this large process could then become part of an even larger process, and you keep getting bigger and bigger units of abstraction to describe the entire program. The other downside to this, though, is that you can't branch. This is a one-path style. You can go from the beginning to the end. And, you know, the only way you can escape is to throw an exception and abort the whole thing. But it turns out a lot of things actually work this way, where you just need to go through a bunch of steps and you need to make sure that you've got them in the right order. This can help you represent them. So there's a variation of this, maybe, that you see a lot, especially in Clojure. I call it the wrapper pattern. And this is the foundation for a library in Clojure called Ring, which is widely used for building web applications. And generally, you see this pattern when there is one main execution path. You know, there's sort of one happy path, but there's a potential to branch off from it at each step. It is actually possible to do branching in general with this pattern, but it's much more confusing and much less common. So it looks like this. You define a bunch of wrapper functions. And rather than being functions directly of the input, these are going to be higher order functions that take a function that operates on the input. And they're going to return a different function that operates on the input. So generally what they do, they take a function as an argument, and they return a function that's going to do something either before or after the function that got passed in. Now, they could modify the input, transform it somehow. They can also modify the output of the function and transform it somehow. They could even decide not to call the function at all, maybe because there's some precondition that failed, and so they don't want to continue processing that piece of input. So then you can combine all these things by basically calling the wrappers sequentially to build up your final function that sort of represents your entire program. So this is, strictly speaking, more powerful than the pipeline pattern. And it will optimize fairly well because this all compiles down just to straight function calls. It has a lot of flexibility because each of these wrappers can kind of do whatever it wants. It could make branching decisions. It could decide, to abort and go do something else. But it's a lot more complicated to think about, to reason about. First of all, just the way this is typically written, it's backwards. So that function, that final function there, is composed of the original function with all these wrappers around it, but the result that you get is actually going to run wrapper C first. Then it's going to run wrapper B, then A, and then eventually it's going to get to your original function. But of course, each of those wrappers could be doing things before or after the call. So they could be doing things at the beginning of the chain or at the end of the chain. So, again, it's very powerful. It's just a lot more complicated to think about. And you can tie yourself in knots trying to reason about the order in which these things actually happen. The other difficulty you can run into here is that if you're making decisions in these wrapper functions, what can often happen is that you have one wrapper for each kind of decision you want to make, and so you end up doing them all linearly. So it's like, is this an X? No, okay, keep going. Is it a Y? No, okay, keep going. Is it a Z? Okay, yes, now I can do something. So whatever your branching, whatever your conditional logic is, it's going to be linear. It's going to do a bunch of checks. You don't really have the option of doing a constant time check in here. But still, it's a very powerful pattern. So this is a pattern that appears in all kinds of languages, not just functional languages. I think it's particularly easy in functional languages. But the basic idea is you have something you want to do. Maybe it's you're going to create some state, you're going to acquire a resource, or you're going to start some process, and you want to be able to cancel that at a later time. You want to undo it. And one way to do this, there are lots of ways, but let's say that in this case, the thing you're doing doesn't have a distinct identity. You can't just, it's not a value that you can pass around. Maybe it's something that gets created in another place, like a thread. So what you can do is create a function that does the thing, creates the thing, acquires the resource, and then returns its undo function, and I call that the token function. So it returns this token that you can use to get back to the thing you created and maybe cancel it, maybe destroy it, close it, whatever. The advantage to this is that, well, one, you don't need a reference to whatever that target was. You don't actually need access to the thing that you created in order to destroy it. And so the thing that controls what you're creating could be in a different piece of code somewhere else. Of course, the downside is you have to store the token. You have to hang on to that return function somewhere. There are lots of variations of this. This is actually how the scheduled thread pool in Java works. You give it a runnable thing, and you say, run this thing at some later time. And it returns you a scheduled task, which you can use to cancel the function before it's been run. Clojure also has a version of this. Clojure has a thing called watches, which can be attached to some mutable reference, something that can change. And a watch, the difference with a watch is, that makes it a little different, is that you supply the token. That's that key argument over there. Now this has the nice advantage that you don't necessarily need to store it. The key could just be a literal value in your program, and then you can just reuse that key somewhere else. But it does mean that if you don't want to do that, you actually have to go to the trouble of generating the keys and storing them. So again, just a very slight variation on that pattern. Now this, of course, brings us to the observer pattern. This is one of the Gang of Four patterns. It's a very famous pattern, and so I'm not going to spend a lot of time on this, but just to show some of the variations that you might find on this pattern in a functional language. There's sort of the classic observer, where you register an observer with some stateful thing, and it gets called, but it only gets the thing. It says, you know, something changed, and then the observer has to figure out what. But you could choose lots of different variations, and I think any one of these might be the right variation depending on your application. So Clojure watches give you the mutable thing that changed, the state before the change, and the state after the change. And then your observer function can decide what to do. They'll also pass in the token that you assigned when you created the watch. I found a slight variation of this that's very useful for driving a GUI or some kind of interactive system, which is to pass the old state and the new state and the thing that triggered the change. So if the event that triggered this change from one state to another was something like a mouse click or, you know, a drag operation, maybe I want to do something on the screen to animate that or show the effect, and I need to know what the event was. You know, I could probably derive that by looking at the old state and the new state, but it's a lot of work. It might be hard to calculate that difference. Much easier if I just pass it in. Finally, there's another Gang of Four pattern, again, a very common one, and this is one of the ones that does sort of disappear in a functional language because we have higher order functions. You have some process or some algorithm, and you want to swap in different variations. Now, in the Gang of Four book, they do this with abstract classes and a lot of complicated stuff, but it's really just passing functions around. You could do this just by passing functions, but you don't always have to do it that way. There are different variations. So here's one variation. This in Clojure is using a protocol, and this is actually very close to the object-oriented approach to this pattern. You have some protocol that represents all the extension points for a given series of operations, and then you're going to have some process that calls those extension points. Now, the biggest advantage to this, well, aside from the fact that it'll perform very well on the JVM, is that it groups the methods together. So I can see that in order to implement this algorithm, well, I have to provide implementations of those three methods. The downside, of course, is that you have to actually create instances of objects implementing those protocols, so it's one more thing you have to deal with and pass around. So in some situations, it might be better to actually use something that's driven off the input data. A great example might be, you know, parsing data, which might come in one of several different formats. Well, you could write a function that's just going to dispatch on the format and choose a parsing function from that set. So you could provide additional parsing functions for your different kinds of input that might not have been known when the original process was written. This works especially well if you have just a single extension point, one thing that can vary in a larger process. But it doesn't give you the grouping that the protocol style does. Now, what some people will do when they encounter this problem, you know, they need something to be extensible with a group of functions, they'll put them all in a map. Now, this works perfectly well, and you know, it does seem very functional. We're passing around functions as values, and they're all in maps, but it does come with some costs. The biggest one being that because it's a map, you have the cost of a map lookup with every function invocation. And in a runtime like the JVM, that's going to prevent a lot of the special optimizations from happening. So this is very flexible because that map is data and you can manipulate it and modify it. But it's giving up some possibilities by giving you all that flexibility, and you probably don't need quite all of that. So I'll leave you with this idea. That is a BBC Acorn. It's an early personal computer, kind of similar to the Commodore 64, I think. And I typed in this Hello World program on it. And that's a pattern. You know, that's something that we're used to seeing. We see it over and over again, and it has meaning apart from just the syntax and the semantics of its execution. So, you know, patterns are everywhere. They're in human language, in programming languages, in the structure of systems we design with those languages, and they can be useful. They're not always, they don't have to be dogma, they don't have to be, you know, big enterprise, scary Java stuff. They can actually help us recognize things or find patterns that would be useful in our own programs. And that's all I have. So thank you for coming, and I've got about 10 minutes for questions. You said the question is, would I consider the consequences pattern with its branching to be a reactive programming system? Yes, it could be, in a way. That's certainly how you could use it. You know, I first saw that in the context of a game system, where we had literally rules of a game that we were implementing. And the rules were, you know, when a player does X, well then, you know, Y, Z, and Q have to happen. So yeah, I think that's a good description. All right, well, thank you for coming. Go have coffee.